Hello, everyone. Excuse me, sorry. Hello, everyone, and welcome to this webinar. This is a micromaterials webinar. I am Dr. Sam McMaster from Surface Ventures. I will be your host today. So just before we get started, I'd just like to welcome you all here and to ask if you could just type in the chat where you're joining from today. It'd be great to see that I'm coming through to you loud and clear. Okay, we can see we've got a good number of attendees loaded in already. Be a good mix of university and company. Christine from Cranfield, welcome. Okay, excellent. It looks like coming through loud and clear, so that is great. Before we proceed, I'd just like to go over a few housekeeping things. So there will be some poll questions released in a moment once I hand over to Ben. So those will be just to find out a little bit more about you as the audience. So please do answer those. They will be, the chat will move over and then the poll questions will be visible. There will be a few of those, and I'll let you know once all of those have been released. Additionally, we have a couple of handouts from Micromaterials on the specific modules that will be discussed today during this presentation. And additionally, we have an attendance certificate, the link for which will be released as we get to the questions and answers during this event. So now, without keeping us too much longer, I'd like to move on to introductions properly. So today, Professor Ben Beek from Micromaterials will be presenting the Random Impact Test, a revolutionary nano impact testing method for simulating erosive wear in coatings and bulk materials. So just like to give a little bit of background on Ben before we hand over to him and bring his presentation up. So Ben did his postdoctoral study at the University of Hull, and he was also at Nottingham and UMest before joining Micromaterials, where he has been Director of Materials Research since 2006. He's a fellow of the IOM3 and a past chairman of the IOP Tribology Group, and is currently a visiting professor at Manchester Metropolitan University and the Universities of Leeds and Huddersfield. Extremely active with lots of collaborative research with other nanotest users, with over 150 published papers and a H index of 35. So at this point, I'd like to invite Ben on stage, and I'll bring on his slides. Okay, excellent. We can hear you, Ben. So at this point, I'll leave stage and all over to you.
Okay, well, thank you very much for the intro, Sam. Very much appreciated. So welcome, everybody. And as Sam said, I'd like to talk this afternoon about our new test for simulating erosion by performing random distributed impacts across the surface. So this allows us to study how damage from one impact event is affecting the next impact event, and how damage between neighboring impacts builds up and causes ultimately erosion and material removal. So the reason why we're interested in this is because we're trying to tackle problems in terms of efficiency in jet engines. So to improve the efficiency of jet engines and reduce CO2 emissions, we need to be able to operate a jet engine at higher temperatures. But the problem with that is that these increasingly high temperatures are causing issues with the thermal barrier coatings that are on the components of the turbine blades in the hot gas stream, which protect the superalloy in the turbine blades, and they are susceptible to erosive damage, which increases at these higher temperatures. So the challenge is, can we design multifunctional coatings that can combine thermal barrier properties with also enhanced erosion resistance? So this is quite a challenge from a coating development point of view, because there's lots of compositions you could try and it's very expensive. and time consuming to evaluate their properties. So what we really would like is to develop novel small-scale test methods that allow us to effectively evaluate and screen potentially useful compositions for further work. So we set up with Cranfield University and Thin Metal Films and the National Physical Laboratory, Innovate UK funded projects, which was called High Temperature Tools for Designing Sustainable Erosion Resistant Coatings. I'm going to be talking today about some of the work that we've done within that project, and it builds on a previous study with Cranfield University where we've shown how we can use our nanoscale impact test technique to look at these thermal barrier coatings. So I'll start off by introducing what I mean by our standard nano impact test technique. Then I'll move on to our new random impact test and show how we've developed it. And we started off looking at reference model systems, bulk materials, and we use that to understand and develop the test technique and understand how the process of the impacts developed and the crack networks develop impact by impact. And then I'll move on to looking at the thermal barrier coatings for the turbine blades. And this, we're going to look at two particular systems. I'll talk in detail about those in a moment. And these are zirconia stabilized, yttria stabilized zirconia, and gadolinium zirconate. And I'll start off just by looking at standard impact tests, where we look at repetitive tests at the same location and show what information we can get about from that. We can, as well as SEM, we can do some focused ion beam milling to look at the subsurface damage, and we can see how well that the impact test correlates with the actual erosion behavior. And we can also look at things like the effective impact angle and also the comparison between these two different thermal barrier coatings. And then for the rest of the talk, then I'll move on to our new test technique, the random impact test, where we're looking at the effects of changing the impact load, the density of impacts, the number of impacts, and how these affect the mechanism. And again, also looking at wear volume and understanding how we can get quantitative information from this test technique. So the two thermal barrier systems that we're going to look at today are E-beam PVD yttria stabilized zirconia system 7SYZ, and that essentially is it's a ceramic top coat with a thinner bond coat, and it's on either mnemonic 75 or sapphire substrates, and similar thickness gadolinium zirconate system, and in this case it's effectively a bi-layer system with a gadolinium zirconate top layer and then a 7YSZ sublayer, and again the same bond layer and similar substrates. So you can see there from these images that these coatings have a very interesting microstructure, and you have these very columnar structure. They both have some porosity, both within the columns and between the columns, and this adds to their strain tolerance. It's one of the reasons why these E-beam coatings are used in these demanding conditions in the engine. So the nano impact test technique, there are two different ways we can run this test. We can run single or multiple impacts. So if I start off just talking about a single impact test, so we typically have a test technique where we pull our test probe away from the surface and then we rapidly accelerate it to create this high strain rate impact, as shown schematically on the bottom left there. And then as it hits the surface, then the test probe bounces and eventually comes to rest. And this happens in a small number of milliseconds. So all of the subsequent bounces are elastic typically, so all of the damage is done during that first bounce. And you can see on the right there is an illustration there with a cube corner probe hitting a bulk alumina sample. you generate these very, very high strain rates compared to a normal quasi-static nano-indentation test where the strain rate might be sort of 0.1 per second or something like that. So we're many, many orders of magnitude higher than that. So that gives us more relevant information for these high strain rate contacts that happen in the real world. So instead of these single impacts, we can repeat that process. So now we're looking now, instead of milliseconds, we're looking at combining repetitive tests now, typically, as I say, at the same position. And then effectively now we've got a surface fatigue test. And this allows us to look at the number of cycles to failure and really start to understand the damage tolerance of these typically coating systems, but also bulk materials. And we can run these tests at room temperature, or we can run them at high temperature as well. And in practice, they correlate very well with erosion tests. So here's just a typical example of the sort of data that you might get off one of these repetitive tests at the same position. So this is actually taken from one of the tests with the cube corner indenter on the alumina sample that I showed the high strain rate from a couple of slides back. And here we can see we've got penetration depth into the material on the y-axis and time on the x-axis. And it's one impact every 4 seconds in this particular test. So we can see we have this very small depth right at the beginning of the test due to the static contact. Then the first impact creates a larger depth, something like 600 nanometers, because the the dynamic force is much higher than the static force. And then there's this very sort of gradually increasing probe depth over the next about 10 impacts. And then suddenly there's a big change in depth. And in this case, this is corresponding to material removal, so the cracking and material removal in the system. So if you have, for example, an acoustic emission sensor, which is actually done in this work, we're not showing it, and you can actually get a distinct peak in the acoustic emission just at that particular impact corresponding to that cracking. And then you can use focus ion beam again to look and see these crack networks that form subsurface. So again, as I say, it's a very powerful test technique to looking at fatigue and fracture. So one of the nice things is it's done within our nanotest system, so it has all of the control that we can set for normal indentation and scratch tests, and we can set up these automated arrays or matrices of measurements. We can do multiple tests, set everything up together at different forces and different number of repeats at different positions. And that allows us to build up a statistical picture of the surface fatigue behavior of typically coating systems, and generate something like an SN curve, but from a single sample. So this is really a very useful test technique. So, and each of these tests, as well as the microscopy that you can see on the right, also has all of the depth versus time data and the number of impacts to failure data associated with that. So you can build up these very accurate pictures of time to failure. So as I said, it correlates very nicely typically with erosion testing. So this is a little bit of a complicated slide showing how we used this test technique in the past for these E-beam PVD TBCs. And in this work with Cranfield, we were looking and trying to understand whether the test technique could simulate the changes in erosion wear resistance that happened after thermal aging. So what you see in the middle is erosion tests that Cranfield did in collaboration with Rolls-Royce. And what they found was that after thermal aging, the erosion resistance of these TBCs decreased. And when they looked under the microscope, in cross-section, they found that this was due to a sintering and essentially both between the columns and within the columns. And this ultimately led to the possibility of more material being removed per impact, and cracks that would form subsurface would then be able to travel more effectively across columns. So some of the strain tolerance in the system was being lost. So we were interested, particularly if we could replicate that with our nano impact test. So we chose the conditions where we would have the right sort of probe size, so that we matched the scale of deformation in both tests. So we noticed that each event was on the scale of the individual columns. And if you see on the right, you can see sort of semi-quantitatively, there's a very nice correlation. Now, this is plotted depth against time, so you could easily convert that to impact volume against effectively, well, I say mass or number of impacts. So this is some work we've done more recently, and this is in collaboration with Thomas, who's now at MMU, and Sam, who you've just heard from in the introduction. And here we were looking about whether we could use the test technique to correlate with sand erosion for diamond-like carbon coating systems that were deposited on a hardened tool steel substrate. So in this case, there are 3 different coating systems. They're all around sort of 3 or 4 microns thick in this case. And just an illustrative result there on the left, where we can see these 3 different coating systems. And the tungsten-doped diamond-like carbon coating system is much more fatigue resistant. So it leads to a lower final depth, whereas the other 2 coating systems that are called A and B there, the undoped and the silicon-doped DLC, those are less impact resistant. There's a transition in sort of failure mechanism, if you like, after about sort of 12 or 13 impacts in those 2 cases. And there's also a transition where the silicon dope one actually starts off being not quite the worst, but ends up being the worst. So it switches over in relative ranking against the hydrogenated undoped DLC. And so Sam did those tests, but he also did some sand erosion tests, and these were individual tests. There's a certain amount of scatter because this is from a large number of tests here you can see on the right. But nevertheless, you can see essentially the same trend, that the coating C is much more resistant to erosion, and the other 2 coatings you can reproduce the ranking, and also you can even pick up that switch that happens between the 2. So what we're doing in our impact test is we're repetitively hitting the same position, and we're seeing these very nice correlations, which is very useful, and we've done this over a number of years. It's very successful. But one of the things we thought was, well, maybe we would like to be able to simulate erosion even more accurately. So if you look on the bottom right there, you can see an image of a surface after one of these tests, which has got about sort of half of the substrate is removed. And you can see it's not a particularly even erosion scar. So this pattern of impacts and erosions, they're happening fairly randomly over the surface. So this sort of thing gave us an idea that we might want to be able to see if we could simulate that by designing a different type of impact test. So we've achieved that by, in software, generating a program number of random impacts between a specified region, any region that we like, and we can choose how many impacts we want. We can choose what type of distribution of impacts within that region, whether they can be totally even probability of any position, or whether we want a sort of Gaussian distribution where the probability is more likely nearer the center of that. So we have complete flexibility, and this allows us then to look at these impact processes a little bit more accurately. So as I said, we used bulk materials as part of the development of this. So these are non-coatings. So we picked typically two different glasses, BK7 glass and fused silica glass. These are both smooth, homogeneous, transparent, and they also have broadly similar fracture toughness as well. And what you can see there is a couple of examples there. There's an optical and an SEM of some cracks on the borosilicate glass. And you can immediately see for this material, you can see some of these cracks between subsequent adjacent impacts, essentially. So these crack networks are starting to build up. So we studied this by changing the number of impacts between 50 and 500. So if we look to start with, I don't know how well you can see that, but on the fused silica, well, we have sort of 50 impacts randomly within this half a millimeter by half a millimeter area. There's not much overlap, but as we increase the number of impacts, then there's more probability of these impacts being closer together, and this causes essentially damage between the things. And you can see progressively as it builds up, and you're starting to get a transition to a more extreme mechanism by 500. So that's on fused silica. Something more dramatic happens when you look at the BK7 glass, and you can see here, even from 50 impacts, we're starting to get networks of cracks already forming between some of the adjacent impacts. And as we run this test on with more impacts, these networks are starting to build up, and these are leading to rather dramatic removal. And at the end of the test, we've just completely destroyed the sample. So this is quite a nice result, because this actually correlates with what you see in the literature for erosion resistance, despite the fracture toughness, that BK7 does have a worse erosion resistance. And if you can see here, you can see there are some very, although the size of the impacts in both cases are about the same, the crack morphology is really quite different. So we used laser scanning confocal microscopy to look at this a bit further. So one of the things we did then was we, instead of using these random impacts, we used a controlled arrays. In this case, we've got 10 lines of 10 impacts set up, and the only thing that's different is the spacing between these impacts. And this, on BK7, under the same set of conditions, then there's cracking throughout the entire range. This is for fused silica, and what we can see here is that as the crack spacing is 70 microns or greater for this set of test conditions, there's no cracking between these different, or no apparent cracking between these sub-adjacent impacts. And we're starting to get, by 60 microns apart, we're starting to get a few of these cracks joining up. So we used, this is the contrast image. So we're also at MPL, they were looking at the green light images, and then that reveals a little bit more about what's going on. So here you can see in the middle there at the top, actually there's a lot more going on in these systems subsurface, and you can see these sort of straight lines between, or curved and straight lines between these impacts that you're not seeing at the surface. And one of the nice things that you can do with this, because these samples are optically transparent, is you can sort of look through the samples, and the LEXT imaging allows you to rotate these things and build up this pattern of what's going on subsurface. And you can see there essentially that what appears to be happening is that it's this interaction of these Hertzian cone cracks that forms these apparent lines that you see subsurface. In contrast, there's an extensive lateral cracking on the BK7 glass. So back to the TBCs now. So to say, well, now we will go on and we'll start off by looking at the repetitive impacts at the same position on these samples. So we'll start off with the yttria stabilized zirconia system. So it's a columnar material, and at the top you can see these columns, and they create a certain roughness. And there's a fib cut on the right, and you can see them clearly sort of looking through, and you can see the columnar structure, and you can see the porosity, and you can see the roughness from the columns. And there's a little bit actually of the platinum there on the top that's just been used as part of the fibbing process. So then we did some micro impact tests on these two different coatings with, in this case, 50 impacts at the same location, and repeated this test 3 times over a range of different test loads and accelerating over 50 microns. And we did these tests at 2 different impact angles. So the spherical probe has got the geometry as shown on the right. So it's 25 micron end radius going into a 90-degree cone angle, essentially. So there's a sort of transition between the spherical part and the conical part that happens after about sort of 7 microns penetration. So when we're looking at these test data, we think it's better to think of these things as sphericonical probes rather than spherical probes if the impact depth is greater than that. So here's a couple of, on the left, a couple of example SEM images, and what we can see is some compaction and some sort of cracking both within, some cracking also within the crater and also at the edge of the crater. And there doesn't appear to be much obvious difference in mechanism across that load range. And if you look at the depth versus time or depth versus impacts, you can see that the trends are relatively smooth. So there's none of these abrupt material removal events like I showed you on the example on the alumina way back at the beginning. So we normally do report impact depth data, but one of the things we thought might be interesting is whether we could directly convert this to impact volume. So provided we can take account of the probe geometry, the sphericonical probe geometry, and correct our depth data for elastic recovery and also the instrument frame compliance contribution, then we essentially get an impact volume that correlates for each of these depth measurements that we've got. So when we do that on the 7YSZ, we can see that we've got these very linear traces of volume versus load, and they go through 0, 0 very accurately. And the correlation coefficients, you can see they're all in excess, R squared in excess of 0.999. So the next step was to look at focused ion beam cross sections through these craters to have a look at the subsurface damage and see how that compares with erosion. So this is an example of one of the impact craters at the lowest load that we looked at, which is 500 millinewtons. And we can immediately see sort of there's a compaction zone in the center of the crater. And then just below that compacted area, then we're seeing a lot of cracking going across these columns. So this is one of the things that's these cracking across these columns that's in some cases being stopped by the columns and being deflected by the columns. And this is one of the things that's leading to material removal. So if we now look at higher force, so in this case it's the same test, the only difference is that the force is 3 newtons instead of 500 millinewtons. And now we can see essentially much more extensive crack network, and we're getting this sort of columnar structure really being broken up now, and then we're getting this sort of transitioning into this much sort of finer scale microstructure and material removal. And what's interesting is if you look at erosion scars, essentially, then you can see similar sort of cracking across columns, if you can see on the right, and also if you're quite near the center of the scar, you can get some more extreme cracking and also loss of the structure, which is sort of as seen on the left. So very similar sort of crack patterns that you see in both types of test. On the gadolinium zirconate, essentially you've got a slightly similar sort of scallops shell type structure, if you like, and again it's columnar. And what I've done on the right is try to sort of highlight, sort of white out that image a bit to try and emphasize some of the columnar structure. And you can see, maybe you can just make out the sort of slight orientation on the 7YSZ, the columns were oriented normal to the surface. Here they seem to be angled more like about 15 degrees away from the surface. So that's a slight difference between these two materials. And that will have an impact both on its thermal conductivity, but also on its potentially on its impact resistance. And when we perform the same tests on the gadolinium zirconate, what we can see here is instead of the smooth sort of curves that we saw on the yttriostabilized zirconia, then we're seeing much more jagged curves in many cases, as you can see on the right. And what appears to be happening is that material is falling down from the sides of the crater into the impact crater during the test, and that's what's causing that. So if you look in the micrographs on the left, you can see a couple of examples, both at 500 millionths and also at 1500 millionths, where you can see either the craters either have debris within them or not, essentially. So there's a lot of variability, and this therefore leads to more variable impact volume data as well. The yttriostabilized zirconia system was not particularly sensitive to impact angle between 90 and 75 degrees, but the GZO system is more impact resistant at the 75 degree angle, and this is more typical of what you might see in a ceramic system, essentially. So many of these step events that you see sort of top left there, there's much less of those events at the 75 degree impact angle. And if you look at the right, I've contrasted the two angles at 75 degree impact in the red symbols there, and you can see that at the start of these tests, they really start off very similar in both cases, but it's the progression of the damage as these tests continue that really marks out this different sensitivity on impact angle. And this indicates potentially that sort of, some sort of column bending may be going on there, and maybe it's one of the things that's detrimental for this GZO system. And again, as I say, we can take the final depth data and we can convert it to impact volume, and then directly then we can get a measure of the relative difference in erosion resistance between these two different materials in our type of test. And again, as I say, the 7YZ system is linear. The GZO system is linear up until certainly to 1 Newton, and maybe at a higher load. Some of this complexity due to the debris falling into the crater, or the debris damage actually taking place outside the crater, and even potentially the sublayer. There are several reasons why that system might deviate at a high load. But nevertheless, it's quite encouraging that there's a very clear difference across the entire load range there. So I finish off with the random impact tests. So we can generate these rectangular distributions, as you see on the right, where we have an equal probability of an impact being anywhere within the test region that we set. In this case, it's 1 millimeter by 1 millimeter. Or we could go for more sort of a different type of distribution, like a normal distribution, where there's a higher probability of those impacts being near the center of the test region, which can simulate certain types of erosion tests more accurately. So if we look at the sort of damage that we get in these random impact tests, now we can see a couple of different images there. You can see that we're getting the same sort of compaction that we see in the repetitive single impact tests, and also that cracking is occurring between these impacts when they start to be too close to each other, essentially. So if we compare the two coating systems by eye, they look reasonably similar. At just at the beginning of the test, you can see these things. They look quite similar. The same sort of mechanism occurring in both cases. What's interesting, though, is if we increase the severity of the test by either doing more impacts, or in this case to do the same number of impacts but over a smaller region. So in this case, I'm contrasting 500 impacts either over 1 millimeter by 1 millimeter or 0.5 millimetre by 0.5 millimetre, or 1/4 millimetre by 1/4 millimetre. And there we see really quite a dramatic evolution of the impact process, where this sort of columnar structure is completely broken up by these impacts. And so you're going from, on the left, you're seeing that columnar structure between the impacts, and in the middle it's starting to be broken up into much smaller pieces, and then on the right you're getting really this sort of filigree type structure. And you end up with a few of these compacted impacts in the end, but most of the original impacts are now being covered up by the debris. And that's not an entirely uncommon situation for an erosion scar, where essentially you're just seeing the result of the last few impacts. So if we can sort of quantify this, in this case we're using the laser scanning confocal again to look at the influence of test load, but also the type of the distribution of these impacts within a region. So on the left we're contrasting a rectangular and a Gaussian distribution at half a Newton. On the right we're doing the same contrast but at a higher load. So what we can see on the extreme left there is that there's a region just sort of towards the top where just starting to get a more obvious fracture mechanism there. And then we can look in the original data and zoom in and find that actually that happened really quite late in the 150 cycle test. If we perform all those impacts more closely together, then we're seeing essentially a much more a larger volume of material is removed. So it was in this case about 2 to 1. If we increase the force, however, then we're getting failure in both cases, and we don't see the same correlation. So it's quite easy to get statistical information there that you can run these tests quite quickly. They don't take very long, and then you can use your laser scanning to get up a quantitative erosion metric for each coating that you're looking at. So if we contrast the two different coating systems now, the GZO and the 7YZ, what we can see here essentially is that there's a much bigger change between these two coating systems. So it's typically around, in the Gaussian ones, typically sort of about 3 to 1, something like that, in terms of impact volume. And this correlates reasonably well with erosion rates, which are maybe sort of a little bit sort of higher than that, maybe sort of 5 to 10 times higher. But that in these sort of short-term tests, it's quite encouraging that there's a reasonably good correlation between these two coating test data. And indeed, if we run these tests on, we would get sort of closer correlation still. So to sum up, hopefully I've given you a reasonable amount of information about our new test technique and give you some of the areas that we've applied it to so far. It's been very successful in that. And we're able to clearly show for all the materials we looked at that the impact density influenced the rate of impact wear or erosion, and effectively that the number of impacts and their spacing and distribution type were all interrelated. So that they all sort of correlate together to give you an overall wear weight. For the two TBCs that we looked at, we were able to see initial compaction was followed by these developing fracture processes, the formation of this fine scale debris followed by these large area brittle fractures. And so that's hopefully going to be very useful information as we go further in the project to try and look at more novel coating compositions that have different microstructures where we're able to design in more erosion resistance. It was nice that we're able to show quite nice correlation between the mechanism and the rate of the actual erosion tests. And I just should say it's also, although I've presented some results, it's also very easy to extend the tests by changing the load or test probe geometry, changing impact angle, and indeed changing test temperature as well. So it's a very flexible test technique. It's all possible within our sort of impact module in the nanotest Vantage system, shown there on the right. So if you're interested in any further information there, I've given a background paper on TBC morphology and how that affects erosion rate, done by John Nichols and co-workers at Cranfield back in 2005. There's a call out there to the paper we did on nano impact of the TBCs back in 2012. I've done a review last year on hard coatings, so that's open access. You're very welcome to look at that there in MDPI Journal of Coatings. And this is very new work, so we haven't published on it yet, but I'm going to talk at the ICMCTF conference in San Diego in 3 months' time, so hopefully I have even more work to present there. So thank you very much for your attention, and I'll finish there. Thank you, Sam. Sam escaped. He's back.
Yep, just reloading my video stream. There we go. Thanks, Ben. That was a fascinating talk. It was great to see. It's like from when I did some erosion testing and correlating with impact. It's great to see this sort of next evolution, then on to actually being able to mimic more of the proper erosion tests with this randomized distribution. So really, really great to see there. So what I'll do right now is for anyone in the audience, if you're interested in an attendance certificate for this, I'm going to share the link to that now. So that should appear down in the bottom left. So please do click on that. What we'll do now is we'll have a question and answer session. So if you have any questions for Ben, please type those in the chat, and we'll try to answer those questions as best as possible. I think for the moment, just whilst people were typing questions in, just a quick one from me to get us started. So you mentioned you're going to look at different coating types, microstructures, and novel coatings. Can you tell us anything about what types of structures or microstructures or?
Well, I think the interesting thing is
you're going to look at
if we can combine retaining the columnar structure, but also with a degree of multi-layering in this plane as well. So it's that combination of those two types of structures, and we may be able to do sort of compositionally vary, have layers of more erosion resistant but less thermally less good thermal conductivity layers. So there should be some optimization based around that. So the challenge is always in these things is that the ultimate material has to be multifunctional. We can't just optimize for the one parameter at the effector. So this is the challenge for the guys at Cranfield University who are working with Rolls-Royce on this to try and develop these multifunctional coatings. So with that in mind, our role in this is essentially to provide lab scale test methods that allow them to effectively screen all of the different possible contributions and allow them to sort of drill down and get to what's the things that they want to look at and develop in more detail.
Okay, yeah, it'll be very interesting to see the future work of the ICMCTF presentation goes well on all of this. Okay, so just like to remind those in the audience, if you have any questions, please do type them in the chats. That's how we normally work this with this webinar platform here, just to address questions from the chat. I think I'll leave the attendance certificate link up for a little bit longer before I switch over to the next link I'm going to share. Just another quick question. Sort of when from my memory of doing a lot of impact testing, one of the things to sort of be careful of is of course, the actual wear of the probes themselves. How much of an effect does this random distribution have on the probe wear? More of a machine question, but
It's a good point. I
that's
think I didn't talk about it much, but actually one of the things that we presented essentially was more microscale rather than nanoscale impact wear, because then we could switch towards these 25 micron probes. And they're 25 micron probes made of diamond, and the geometry of these things is remarkably durable. Yeah, they can handle sort of many thousand impacts without changing their geometry, or many, or potentially even sort of hundreds of thousands of impacts. Whereas I think if you had a very, very sharp cube corner impact probe, I think then you might have to be a little bit more cautious. But as I say, one of the advantages where we extended our test capability to go nano and micro was this ability to do these higher blunter probes, but also it allowed us to put more impact energy in, so we could accelerate higher force, but also to accelerate over a further distance as well, so much higher impact energies.
Okay. Very interesting. We've got a question and a comment here from Gyuji from University of Leeds. I hope I've pronounced the name correctly. Who has asked, may I ask what's the parameter that the random impact can give to evaluate the impact resistance?
Well, I think,
and
yeah,
sorry, Ben, can I just read out the quick quick comment there just to make sure. So sorry, I might not get the idea you are talking about. Like for adhesion, people use critical load for the evaluation of adhesive strength.
Yeah, sorry, sure. So there's several things that you could look at, but I think the thing that is simplest in this case is to have an impact volume, essentially. So that impact volume at the end of the test. So you basically, just as you have in an erosion test, essentially. So you have comparative impact volumes as a quantitative metric that says this is the erosion resistance, and that allows you then to directly correlate between different materials when you look under the same set of test conditions. You see the adhesion, LC and scratch testing, I see you've put in there. I mean, that again is a parameter that is very, again, is typically very sensitive to things like probe radius, also coating thickness and things like that. So I personally, I think LC is a particularly, it's quite a useful metric comparing between different coatings, but it's often very little to do with actual coating adhesion. For that reason, so there's a lot of things behind that parameter.
Yeah, it's one thing just to be aware that if you think about adhesion as like how can you basically pull a layer off a surface when you're scratching into something, you're actually adding like a reasonably complex loading and stressing to the coating structure. So you kind of need to think about that. But So there's a question here from Doris who has asked, do you prefer the rectangular or the Gaussian distribution for impact distribution? Well,
we're still learning with this test technique, but I suspect that the Gaussian is effectively more, at least quicker. I think you're going to get more damage more quickly with Gaussian, but whether it's I think in certain erosion situations that are impact, then these sort of gas gun type erosion tests, those sort of do produce these sort of situations where there is a sort of natural Gaussian distribution of impacts. So I think you simulate those more accurately by doing that. But I guess in terms of other sort of damage situations, maybe rectangular are better. So I suppose it just depends on exactly what you're trying to simulate. It's not really an answer, but I think typically you want your test to be able to start moving into these more fracture modes, and you're more likely to get those for the Gaussian distributions.
No, I think that that answered it very well. It's like you say, it's a new test technique, and it's still sort of defining, I think, some of the parameters for that.
I mean,
First,
and
just said thank you for the
it
response.
might be
One,
that I mean, for the glasses that we looked at the beginning, the rectangular seemed to be very informative as well. So I wouldn't like to say it, I guess. Yeah.
just curious about the rectangle. I wonder whether there's any how much can sort of be gleaned by looking at for different materials, looking at that um, the impact spacing, because there's quite interesting crack morphologies that occur depending upon the spacing that you get for those. So
Yeah, I touched on that, didn't I, with the laser scanning confocal, and I only really showed in detail that the fused silica. But yeah, there's a lot of information there in terms of how these things join up. You definitely, there seems to be almost like there's a critical threshold, I guess.
yes, yeah, we have a question from Rohit Sajan who asks, are these testing methods suitable for any type of material, such as metals, ceramics, and polymers?
We haven't tested polymers yet. We certainly have tested a few metals as well and ceramics as well. And these things are equally suitable for all that. So the impact test itself has been tested effectively on polymers, because you can use metrics such as energy damping and use that. Particularly useful viscoelastic materials, you might have sort of high strain rate differences in energy dissipation that allow you to sort of design more protective materials. That we have sort of customers working on those sort of applications for sort of device layers and also multi-layer paint systems and things like that, where subsurface damage might come into it. But the random impact test, I hadn't really thought about for polymers yet. Maybe that's something to think about. But in general, yeah, these is a very sort of flexible test method. It can sort of potentially work on just about anything, really. Because you can tune your test conditions, you can tune your load, you can tune your accelerating distance, you can tune your probe geometry, suit to whatever type of material you're looking at, essentially.
And it can work up to high temperatures as well.
Yeah, the random impact we haven't done at high temperatures yet, but there's no reason why not. It's fully integrated with the system, and we've certainly done micro impact up to 600 degrees perfectly happily on hard ceramic coatings, and seeing some quite clear differences with microstructure on those. And I think that's the sort of thing I think it would be quite easy to have a look at, and certainly it's one of the things in the project that we do plan to do. We're about halfway through this project at the moment, and sort of as we finish it off, that's one of the things we'd hope to look at.
Yeah, it'd be very exciting to see the results from that. Okay, I'll just wait for another moment or two to see if there's any other additional questions. What I will do now is to just share as well the link to the Micromaterials LinkedIn page. So if this will be a useful resource for anyone to look at. Generally, it's a lot of advertisements of technical talks such as this, and other information about micromaterials product offerings and various capabilities and so on. So I would encourage everyone to look at that. You'll find advertisements later for more talks such as this. Okay, a question from Doris here. Once again, who has said, I'm new to the field. Is the instrument itself a specific instrument for impact testing, or is it a nano indenter used in a harsh mode?
I think essentially it is a nano indenter used in a harsh mode. So we have the Nanotest Vantage system is essentially a multifunctional nano indenter system for nano indentation, also various tribological things such as scratch testing, reciprocating wear testing, fretting testing, and also impact testing. So what we've done here is we've taken our impact module essentially and developed and expanded the test capability of that and use that module to run all of these tests essentially. So these are multifunctional systems, and customers choose which configure their systems for whichever modules they need, essentially. So.
I love the ever heard the term harsh mode?
Yeah, I hadn't heard that before. It's quite good, actually.
That's great. That's a great way to to think about that. Okay, so I think that is it for the questions for this session. So I think with that, let's begin to draw the event to a close. So just a reminder for everyone that is here, you will receive an email later from Demio, this webinar platform, containing a link to the recording of this webinar, so you can watch it back later. And then additionally, I think this will be hosted on the Micromaterials website later as well for others to view, but that will be a check the Micromaterials website and also the LinkedIn page, of course. So yes, with that, let's bring the webinar to a close. So thank you very much, Ben. Fantastic presentation.
And thanks for the hosting, Sam. Much appreciated.
Thank you. Thank you, and thank you everyone for joining us for this session today. Fantastic questions. Always great to sort of get this audience perspective as well. So yeah, please be on the lookout on the Micromaterials LinkedIn page for more webinars such as this. And with that, we'll say goodbye and thank you all for attending.
Okay, thanks so much. Bye-bye.
Goodbye all.